Good morning, students. This is Ms. Medina, and I am recording the lesson on exponential growth and decay word problems. Okay, so when doing these problems, we're going to encounter two situations, okay? If we encounter growth, we're going to use this form of the equation, y equals a 1 plus r raised to the x. In this case, it might be time, whatever it is, that's our variable, okay, our input. The things to remember from here are going to be that a is equal to our initial value, right, if I can color that red. This whole thing right here in blue is equal to b, and this is the growth factor since this is a growth problem. But then this right here will be the growth rate. In decimal form. Okay, and for those of you that don't remember how to go from decimals, if it's 1%, all you have to do is 1 times 100 or move the decimal twice to the right. Oh, oops, I just did that wrong. I'm sorry. If you have something like 1%, where's the black ink? Right, you take 1 and you move the decimal twice to the left, and that's how you end up with a placeholder. All right, another thing to do is just do 1 divided by 100 in the calculator, and it'll give you the 0.01, okay? That's the decimal form. Something like 8% would then be 0.08. Something like 14%, right? You have 14 and you move the decimal twice, that's where you get 0.14. And so please be careful. If you have 150%, then you take 150 and you move the decimal twice over, and that's where you get 1.5 as a decimal. Clear, clear, clear? So please don't mix this up when you're doing this. A safe way would be to always just divide it by 100 and it'll give you the percent in decimal form. Right, the other thing is when you start from a decimal, right? So if your decimal form, and this will be your percent form, if they tell you that it is 0.003, then what you do is you move the decimal twice, and this time to the right. So you move it 1, 2, so this will be 0.3%. Yes, a decimal can be a percent. Are we clear? If they tell you that it is 0.08, right, and then you move it twice to the left, then that is 8%. If they tell you that it is 0.36 in decimal form, then you move the decimal twice, and that's where you get 36%. If they tell you that it is 4.3 in decimal form, then when you move the decimal over, you're going to need a placeholder. So this will be 430%. All right, so I hope that that's a quick review on how to go from percent to decimal, decimal percent. And if we have decay, then the equation is going to look like this. Y equals a 1 minus r raised to the x. And same thing, a is going to be our initial value. 1 minus r, it's still b, but this time we call it the decay factor. And r becomes our, what can we call it? What is it? Decay rate. Once again, when we put it in the formula, it has to go in decimal form. All right, so let's get started and let's see that if I can help you make sense of this. The world population in 2000 was approximately 6.08 billion. So this is the starting point. So this is what we call time equals 0. The year 2000, okay? So when time equals 1, it would be 2001. When time equals 10, it would be 2010. So this is the starting point. The annual rate of increase tells you that this one is going to be growth, was about 1.26%. This is in percent. And in decimal form, it would be 0.0126. This is the rate. I apologize. The annual rate of increase was about 1.26%. Yes, that's the rate. Because it says so right here. My bad. All right, so this is R. Find the growth factor for the world population. Well, we know that since this is going to be rate of increase, we're going to be using y equals a 1 plus r to the x. The growth factor, as we said before, is the whole thing, 1 plus r. So then our growth factor b is going to be 1 plus 0.0126, or just 1.0126. Suppose the rate of increase continues to be 1.26%. Write a function to model the world population. So then this is the basic model, and we just need to substitute in the information. For A, that's going to be the initial amount of people, 6.08 billion. We know that B is equal to 1.0126. And so this equation will be y equals 6.08, 1.0126 raised to, instead of x, we're going to use time, okay? So then that would be the equation for this answer. Let x be the number of years. Oh, well, okay, x, t. Let t be the number of years past the year 2000. Find the world population in 2010. So if it starts at 2000 and it's 2010, right? 2010 minus 2000 means that 10 years have gone by. So t equals 10. So then y equals 6.08. 126 raised to the 10. And this is what's going to go into the calculator. Okie dokie. Let me see. I didn't want to change screens, but I'm going to. Here we go, www.desmos.com scientific. I can't make it smaller, so 6.08 parentheses 1.0126 raised to the 10. All right, since they gave me 6.08 billion as the starting point, I'm going to take this number with 2 decimal points. 6.89, since it's followed by a 1, it's just going to stay at 6.09. 6.89, I mean. So after 10 years, we will have the world population of 6.89 billion. All right, so they've asked us to identify, this is the rate right here. That's the growth factor. That's the equation. And that's the population after 10 years. Next problem. A computer valued at 6,500 depreciates at the rate of 14.3% per year. All right, so then this right here, where's my pen? This right here is going to be the initial value, or the y-intercept. Okay? When this is graphed, this is the y-intercept, RA, correct? Depreciates at a rate of 14.3%. So we know the rate, R, is equal to 14.3%, or if I move the decimal twice to the left, it's going to be 0.143. Let me erase that. A lot of you guys don't like that 0 in front of it, but I do. Okay. It looks weird when I don't put the 0 behind it. So that's the rate, and they want us to write a function that models the value of the computer. So then that means that we're following y equals a 1 minus r raised to the x. Now, we don't have to write it as a factor. We can leave it as 1 minus r. So then it'll be y equals 6,500, 1 minus 0.143. Okay. I'll leave it as x. But technically it should be time, because it's per year. So x represents years, or t represents years. Find the value of the computer after 3 years. So we know that in this case, x is going to be equal to 3, which is time, right? And then we just substitute it in. I'm looking for the calculator. Okay, clear the 6,500, parentheses 1 minus raised to the 3. Well, since they gave us the initial value at 6,500 with no decimals, then we are going to give them the answer without any decimals. Clear? And if I look at it correctly, it was 4,091. So after 3 years, that will be the value of the computer. It depreciated, so it's worth less. The population of a certain animal species decreases, so we know this is a decay function, at a rate of 3.5 per year. So we know that R equals 3.5%, or if we move the decimal twice to the left, it's 0.035, right? 1, 2, with one single placeholder. We know it's decay, so we're going to be using y equals a 1 minus r raised to the x. You have counted 80 animals in the habitat you are studying. So then our initial value a is going to be 80. Write a function that models the change in the animal population. So it's y equals 80, 1 minus 0.035 raised to the x, where x represents years. Graph the function. What? Estimate the number of years until the population first drops below 15 animals. Okay, so if we just go to decimals and graph this one. see, so www.desmos calculator. So y equals 80, 1 minus raised to the x. Well, the y-intercept happens at 80, and right now my y value is at 10. Okay, so then I need to find 80. 60, 70. Okay, I don't know if you guys can see it, but that's at 80. And, oh, y'all can't see it. Why? Okay, y-axis is going to start from that, and it's going to go to, let's say, 100, so that I can see this. And then how many years? 15 animals. So I don't know. We'll do 40 years. That's good. So what I did is I was changing the axis. So this is the origin, 0, 0. That's the y-intercept, 0, 80. And after 20 years, we have 40 animals. After 40 years, we have 20 animals. And I still need to find 15. Okay, so that's 50. So this is 10, 20. So here in the middle would be 15. Ooh, I guess around 45 years. Oh, look, if we trace it, right? At 10 years, we have 55 animals. At 20 years, we have 38 animals. At 34 years, we have 23. And at about 46 years, we have 15. So there you go. Okay. I don't know if I can click just about anywhere. I can't, but if I keep on pressing it, the population. So after about 46 years, we're going to have less than 50 animals. So this little squiggly tilde is going to be about. So at about 46 years, the population of the animals will be 15. Write an exponential function to model each situation. Find the value of each function after 5 years. Okay. So we know that x is going to be equal, x or time is going to be equal after 5 years. At $12,500 car depreciates 9% each year. Okay, so this is the initial value. So we know A equals 12,500. 9% is the rate. And if we write this as a decimal, we move the decimal place over. Okay. And we're going to be using y equals a 1 minus r raised to the x. So this is y equals and then find the value of each function after 5 years. So this is write the exponential function. That would be the exponential function. And after 5 years would mean that we substitute in 5 for x. Okay. I automatically go for my calculator, but I want to show you guys what it looks like, so I have to do it on the computer. 12,500 parentheses 1 minus raised to the 5. Since they started with a value of 12,500 that has no decimals, so I'm going to round this to whole numbers, so it's 7,800. So after 5 years, your car that originally cost you 12,500 is now worth 7,800. Actually, this is a car that retains its value very well. A baseball card bought for $50 increases 3% in value each year. My brother used to collect baseball cards. I think he still has some of them. He had them all wrapped up in this hard plastic. I don't know if you guys still collect baseball cards, but it was a big deal back then. All right, $50. So this is the initial value. So we know that A equals 50. The rate equals 3%. And if we turn that into a decimal is 0.03, right? Twice to the left. And in value each year. And we have to find the value of the function when x equals 5. All right, so the function is going to be y equals, oh, this is increase. So this is going to be growth. One plus r. So y equals 50, 1 plus, and then you substitute into the equation to find the answer. Ha ha ha, it doesn't work. I was hoping it was going to work. Get rid of this. So it would be 50. That thing was popping up because I was using my pen. So I have to use the mouse. Since they started with 50, which is a whole number, we're going to round this to a whole number. 57.9 becomes 60. Lord have mercy. 57.9 becomes 58. You should know that it's early in the morning. Here we go. That's not bad. That's not bad, I guess. A new car that sells for $18,000 depreciates 25% each year. Write a function that models the value of the car. Find the value of the car after 4 years. Depreciates means that we're going to be using 1 minus r. That one is going to be 18,000. The rate is going to be 0.25. So when they want the equation, it's just this. If this is multiple choice, then they might show it like this. Right? Because 1 minus 0.25 is equal to 0.75. So they might simplify it. So please be aware of that. And to find the answer, we know that x is going to be equal to 4, or time is going to be equal to 4. And put it in the calculator. Mm, 5,695. What? Lord have mercy. your car is practically worthless after 4 years. Make sure you don't buy a car that depreciates 25% each year. You're probably not even done paying the car. You're gonna owe more than the value of the car. Oh. All right, so a new truck that sells for $29,000 depreciates 12% each year. So depreciate means that this is going to be decay. So it's going to be 1 minus R. 29,000 is the original value, initial value. Y-intercept, the rate is going to be 0.12, so we have to put it in decimal form. And we want to know the value when x equals 7. Okay, so the first question is write the function. So y equals 29,000, 1 minus 0.12. And if this is a multiple choice question, it could look like this. What's 1 minus 0.12? Okay, 0.88. And then we're going to plug in the x value, which is a 7. $11,852. There you go. So your car started off with a value of 29,000, depreciating 12% each year. After 7 years, your car is worth about $12,000. The bear population increases. Yay, a growth function. So this is going to be 1 plus R. Rate of 2%. So that means that R is equal to 0.02. The bear population this year is 1573. So the initial value. Write a function that models the bear population. Y equals. Since the growth rate is only 2%, that's a very small increase, okay? How many bears will there be in 10 years? So we know that X will be 10. I wonder how many little cubs we're gonna get. How many do you think we're gonna get? Oh, that's a lot of cubs in 10 years. Rounding to a whole number, so 1917. Look at that. Wait, 17 or 71? Am I getting 1917? That's not bad. That's about a 300 bear increase in 10 years at a 2% increase per year. Okay. An investment of $75,000 increases at a rate of 12.5% per year. Find the value of the investment after 30 years. Okay, increases. So this is growth. 1 plus R. And this is repetitive because I want you to memorize it basically. A is going to be equal to 75,000. The rate is 0.125 raised to the x. And we want to know the value of the investment after 30 years. So we know that x is going to be 30. So we have to plug this into the calculator. So if it's increasing, that means we're going to have more money than $75,000. Well, first I want to have $75,000, which I don't, but here we go. 1, 2, 3. 1 plus 108,871. I mean, for doing nothing and just leaving the money in the bank for 30 years, assuming that your rate of increase 12.5% is constant, it looks like you'll have about $110,000. But what kind of an investment has a 12.5% per year growth? That's a really high growth rate for an investment, unless you get like really, really lucky. And still, it doesn't really grow that much. I mean, really, you should at least, if you're gonna leave your money untouched for 30 years, you should at least have $1 million when it comes out. Just say. I mean, that's for my needs so that I can retire. All right, of a non-existent $75,000 that I don't have. The population of an endangered bird is decreasing at a rate of 0.75 per year. There are currently about 200,000 of these birds. Write a function that models the bird population. How many birds will there be in 100 years? Well, if it's decreasing, that's kind of dangerous. Climate change, we need to be more aware of these things. All right, this is a decrease, so it's going to be y equals a 1 minus r. Initial population is 200,000. Now this is the rate, and in decimal form, you got to move it twice to the left, so we're going to get 2 zeros. 1, 2. So that's the function that models the bird population. How many birds will there be in 100 years? That means we have to plug in 100 for x. Calculator. Oh, I was like, why is this number increasing? Do y'all see the mistake that I made? It has to be raised to the 100. Whew. I was like, number shouldn't be bigger than 200,000. Okay, there it is. 94,207. Yikes. We've lost more than half of the population of the birds, because half of it would be 100,000, and this is under 100,000. In 100 years, I don't think they will really survive another 100 years. And that's what's called is animal extinction. All right, so what did you guys think? All right, and we'll do half-life another day. All right, let me finish this video.